Okay, now with the R estimate that we can obtain from our sample, which is equals to the y bar divided by x bar, and with the variance of our R that we can construct from the estimation, we can construct the 95% confidence interval of our R estimate. That equals to R plus or minus to the critical value multiplied to the square root of the variance of R. Like we previously proved, the variance of R cannot be obtained from the true value of sigma R squared. We can estimate it using our sample SR squared. SR squared depends on our sample data, which is yi minus rxi taking square, adding up together of all the n data point divided by n minus 1. Or that's equals to sy squared minus 2r sxy plus r squared sx squared. When we're trying to look at the ratio estimator, we can see that variance or the standard error depends not only on the y data, it also depends on the variance of x, also the covariance between x and y data. In the formula, we also need to obtain the true population x bar, or the true population mean of x. If this is not given, sometimes we can use our sample x bar to estimate that. Let's look at one example. Food cost. A newspaper conducted a survey of the food costs by taking a simple random sample of 48 basic food purchased in a large supermarket. So prices record on two separate occasions, 3 months apart. Let x bar equals to the average price of 48 basic food 3 months ago. Y bar would be the average price of 48 basic food right now. If we compare the ratio, which is R equals to y bar divided by x bar, that gives an indication of the change of the basic food price. And some additional data was given. So we want to estimate the change of the food price in the 3 months period of time. So R equals to y bar divided by x bar equals to 1.06. So in other words, there's a 6% increase in the food price during a 3 month period. Whether this 6% is significant, let's try to conclude that with a 95% confidence level. With 95% confidence level, the critical value is 1.96. Then we need to calculate the error bound of this estimate. That's equals to 1.96 multiplied to the standard error of our ratio estimate. Standard error of our ratio estimate, like the square root of the variance of R, or the estimated variance of R. Okay, so that equals to 1 over x bar square, but we don't take the square here because we're looking at the square root of it because we have the standard error of it. So 1 over x bar multiplied to the square root of the finite population correction factor multiplied to SR squared over n. X bar, we are not given for the population, so we use our sample x bar to estimate it. So that becomes 1 over 11.41. Finite population correction factor, we don't have the total population size capital N, so we assume that it's very large. So we ignore that, equals to 1. And SR squared over N. SR squared could be defined as what we can have in the information given, that we can use formula 3.26 because we were given a summary of all the summations. So we tried to use 3.26. So we use these data to substitute into the equation 3.26 and then divided by n minus 1. Okay. So we have summation of yi squared minus 2r, summation of xi yi plus r squared, summation of xi squared. R is obtained from part A, 1.06. Since we're given all this, so we can substitute that into here. And the entire calculations, we get 588.566 divided by n minus 1, which is 47. And that bit equals to SR squared. Okay, so don't forget to divide by n minus 1 if we're doing this equation, this approach, and also divide by n. Then standard error of R equals to 0.04477. With the 95% confidence interval for my ratio estimate 1.06, that goes from 0.97 to 1.15. Since this range includes 0, that may imply that could have a minus 3% or 15% increment of the price change. So we may not be able to conclude the price is always go up with this 95% confidence interval based on our data from the sample. What if the newspaper reports that a researcher is expecting a food cost to go up to 12%? What is the statement in terms of the confidence interval? So with that, go up to 12% from our data 1.06, so that could go up by 6% or down by 6%. By standardizing this probability, we find the critical values is less than 1.34 on the both side, two-sided. We can find the probability is about 82%. Example 3.18. An experimenter was investigating a new food additive for cattle. Midway through the 2-month study, he was interested in estimating the average weight for the entire herd of that 500 steers. But he decided to only sample 12 of them. So we have a sample size of 12, and we are given the true population X bar average is 800 pounds. Again, we're given a whole set of the summary of the data. And also, we were given the 12 samples data. So this is a very good example that we can show you how we can calculate the R based on the given information. First of all, we can take the average of Y from a sample, and we can also take the average of all the Xi from the sample. So we have Y bar and X bar from the sample. If we use Y bar divided by X bar, we can find our sample R. R is a constant using our ratio estimator. Then we can calculate a new column called the Yi minus R that we just calculate, multiply to Xi. And we can use that Yi minus R times Xi, and we create the entire columns, calculating the mean, and we find that this mean usually would be equal to 0 if R is an unbiased estimator for the population mean. And SD is the standard deviation of this column, which is equal to SR. Okay, if this data is given, then you don't need to calculate SR square because SR is already given here. So we need to take this square to become SR square. So the estimated variance of R will equals to 1 over population mu x square multiplied to the finite population correction factor times SR square, which is given, divided by n. Everything is given, then we can easily estimate the variance of R. Or we can use, like this previous example, we can use formula 3.26 to estimate the estimated variance of R. They should come up with the same solution. Okay, so after all, we may ask, after the ratio estimator, what I can make use of it? Like my written notes, that we can use the ratio from our sample, R, to multiply to the true population mean X bar to estimate the Y bar using ratio estimator. So in other words, from this example, we can use our R, which is equals to Y bar divided by X bar from the sample, multiplied to the true capital X bar to estimate Y bar using ratio estimator. This expected value of this Y bar R is an unbiased estimator for the population Y bar. Then we can compare this ratio estimator from this Y bar estimation from ratio estimator with the ordinary Y bar estimation from the summation of yi divided by n. With this, we can also estimate our variance of the Y bar. That's equals to X bar squared multiplied to variance of R. Again, we can obtain the variance of R from the equation 1 minus finite population correction factor multiplied to SR squared over n. Then the X bar squared was cancelled out. In this case, we have 12 out of 500. And the SR, we can simply copy from the example from the data listed here. So we can compare this variance of Y bar obtained from ratio estimator with the variance estimated from the ordinary estimation. Under the ratio estimation, this is very important that we plot out the data of the X and Y. When ratio estimation is used, the estimates of the variance and the sample size are quite sensitive to the data points. If they do not fit into a straight line, using a ratio estimation could be quite dangerous. It is very important to plot the data and look for this unusual data before we proceed with any analysis. We need to find they have a linear relationship between the Y data and X data. So for example, this point, or some of the point out here, they could be an outlier. So we need to check them before we really go into the estimation.